Beneath an ancient lake bed, a NASA rover has found something that nobody expected. A pattern of minerals buried in Martian mud, and a rock sample sealed in a tiny tube that might hold the answer to whether we have ever been alone. This is data collected by a 1-ton robot that has spent 5 years crawling across Mars and sending back findings that scientists still cannot fully explain. So, let's go inside. On February 18, 2021, a spacecraft carrying a rover the size of a small car called Perseverance touched down inside Jezero Crater, a basin roughly 28 miles across, sitting just north of the Martian equator. Scientists had selected this landing site because from orbit, 2 features were immediately visible. Carved into the western rim of the crater were channels that looked unmistakably like ancient riverbeds. And spreading out from one of those channels across the crater floor was a fan-shaped deposit that looked exactly like a river delta. Now, a delta forms when a river empties into a standing body of water. As the current slows, it drops its load of sediment. If that is what happened at Jezero, then this crater was once filled with a lake. The first images came back to Earth about 11 minutes later, a silent, frozen desert stretching to a flat horizon under a butterscotch sky. But beneath that silence was a geological record billions of years old, and Perseverance had come to read it. Before the geology mission could begin in earnest, something historic needed to happen first. Tucked underneath the belly of Perseverance, folded into a space barely larger than a tissue box, was a tiny helicopter. The helicopter was called Ingenuity, and on April 19, 2021, it lifted off the Martian surface and hovered at a height of 10 feet for about 30 seconds before gently setting itself back down. It was the first powered, controlled flight on another planet. Some called it a Wright brothers moment. Ingenuity was designed to make no more than 5 test flights in 30 days. But Ingenuity also did something the engineers had not originally planned. On its 26th flight, on April 2022, exactly 1 year after its first flight, Ingenuity was directed to photograph the landing hardware that had been jettisoned during Perseverance's descent the year before. The parachute and the conical back shell had been discarded at an altitude of about 1.3 miles and hit the ground at approximately 78 miles per hour, about a kilometer northwest of the landing site. Ingenuity captured detailed color photographs of the debris. The images were extraordinary. The supersonic parachute, stretching 70 feet wide, was draped across the Martian soil, and though only about a third of the canopy was visible in the images, it showed no signs of damage from the supersonic airflow during inflation. The backshell lay nearby in pieces, which was expected given the speed of impact, but its protective coating appeared to have remained intact during atmospheric entry. Many of the 80 high-strength suspension lines connecting the backshell to the parachute were visible and also appeared intact. Engineers working on the Mars Sample Return program had specifically requested these images. They needed to understand how the entry, descent, and landing hardware performed, because a future mission would need to use similar technology to launch samples off the Martian surface and send them back to Earth. But the debris field told another story. As Perseverance drove northwest through a region called Hogwallow Flats, the rover began spotting strange, bright objects on the ground. Small, shiny fragments that did not look like any Martian rock. On April 16, 2022, a bright speck appeared in a Mastcam Z image of the surrounding hillsides, about 400 meters to the northwest. It covered 6 pixels in the fully zoomed image, corresponding to roughly 15 centimeters in size. The team gave it a descriptive name, bright material. Nobody knew what it was. Later that morning, the entry, descent, and landing hardware team at JPL confirmed it. Perseverance had photographed a piece of multi-layer insulation, likely from the sky crane. The dot pattern on the material matched the thermal blankets installed on the spacecraft. Subsequent images showed the piece snagged on a rock, flapping in the Martian breeze. The sky crane had crashed 2 kilometers to the southeast. So how did this material get all the way to Hogwallow Flats? The answer was simple: wind. The thin Martian atmosphere still moves, and over the course of days or weeks, it had carried lightweight debris across the surface. By July 2022, the team had catalogued roughly half a dozen pieces of suspected landing debris in the area. Thermal blanket material, Dacron netting, a ball of knotted, string-like material that blew directly underneath the front of the rover on July 11, 2022, before the wind carried it away again. The hardware teams suspected it was another piece of shredded Dacron netting that had been subjected to strong forces during the sky crane's crash. It was a strange and humbling detail. On a planet with no human presence, the wind was slowly scattering pieces of the machine that had brought the rover there in the first place. The first litter on Mars. And a reminder that even in the most alien of environments, physics works the same way. Now, the geology. The first major terrain Perseverance explored was the floor of Jezero Crater. And what it found there was not what everyone expected. Jezero is a lake basin. You might expect the floor to be covered in fine-grained sediment deposited by the ancient lake. Clays, silts, the kind of material that settles slowly through standing water. But instead, the crater floor was covered in igneous rock, lava flows, solidified magma. This was not entirely surprising. Mars has a long history of volcanic activity. It is home to Olympus Mons, the largest volcano in the solar system. But finding lava on the floor of a lake basin told a specific story. At some point after the lake dried up, volcanic activity flooded the crater floor with molten rock. Perseverance investigated 2 distinct formations on the crater floor. The upper one, called Mars, was interpreted as a series of lava flows. The lower one, called Saita, revealed a particularly interesting texture through an abrasion called daubs. It was a poikilotic texture, characteristic of an olivine cumulate. That is a rock that forms when olivine crystals settle by gravity out of a slowly cooling body of magma. Think of it like snowflakes settling to the bottom of a pond, except the snowflakes are crystals and the pond is a pool of molten rock. This mattered for 2 reasons. First, igneous rocks can be dated. When a rock cools from a molten state, its radioactive elements start their decay clocks. If these samples are ever analyzed in a laboratory on Earth, scientists could determine precisely when this volcanic activity occurred, anchoring the entire geological history of Jezero to a specific moment in time. Second, even these igneous rocks showed signs of water. The minerals had been altered, changed by interaction with liquid water at some point after the rock solidified. Not dramatically, but enough to prove that water was still present in the subsurface even after the lake was gone. The ground beneath Jezero was wet. The rover collected samples, sealed them in titanium tubes, and began its climb toward the delta. This is where the mission shifted from interesting to extraordinary. As Perseverance ascended the front face of the Jezero Western Delta, it entered a geological record that was unmistakably shaped by water. Every rock told a story of flow, deposition, and time. At the base of the delta, the rover encountered a formation called the Shenandoah. Here, soft, deformed sandstones and mudstones recorded the distal reaches of the ancient river system, where fine sediment settled in calm, low-energy conditions. One particular horizon within the Shenandoah, informally called the Hogwallow Flats member, consisted of mudstone, true lake-bottom mud, the kind of material that forms when water is barely moving. This was direct evidence of the calm, standing lake that orbital observations had long predicted. Above the mudstone, the sediments coarsened upward. Fine sandstones gave way to medium sandstones. Then to conglomerates, rocks made of rounded pebbles cemented together. These coarsening upward sequences are characteristic of a prograding delta. As the river continued to deliver sediment into the lake, the delta built outward, and the coarser, higher energy material migrated on top of the finer, quieter deposits below. Higher still, in a formation called the Tenby, Perseverance found steeply dipping beds of sandstone and conglomerate. These were interpreted as delta mouthbar deposits, the very front face of the advancing delta where sediment was being dumped into the standing water. Similar features were observed at a small, isolated butte called Kodiak, which preserved a textbook cross-section of a Gilbert-type delta, complete with top-set, foreset, and bottom-set geometries. Together, these observations told a remarkably coherent story. A river had flowed through a valley cut into the crater rim. It had emptied into a lake. Over time, as the lake level dropped, possibly during a transition from an open basin with an outlet to a closed basin where water was lost only to evaporation, the delta had prograded outward and downward, chasing the receding shoreline. At the very top of the delta, the rover found something rougher, unconsolidated boulders. Coarse, chaotic deposits suggesting high-energy, late-stage floods. The final gasps of a river system that was running out of water. The rover collected samples throughout the climb, each one a chapter in the story of a dying lake on a dying world. But the delta also held a mystery. The chemical composition of these sedimentary rocks differed from what scientists had seen on the crater floor. The delta sediments showed clear fractionation of iron from magnesium and manganese, indicating that the source material had been processed under particular chemical conditions. The rocks told a story not just of water, but of a water cycle, rain, or something like it, falling on exposed rock outside the crater, weathering it chemically, and then rivers carrying that weathered material down into the lake. Scientists were also able to use the delta deposits to estimate how the lake level changed over time. The progressive downstepping of delta foresets in the Tenby Formation, combined with the Gilbert-type geometries preserved at Kodiak Butte, pointed to a lake in regression. The outlet channel that had once regulated the lake level at a stable height eventually lost its hold. The lake shrank, the river kept pouring in sediment, and eventually the whole system shut down. The samples collected from the delta now sit on the Martian surface in sealed titanium tubes, each one a time capsule from a world that bore an eerie resemblance to early Earth. But the most important chapter was still to come. Between the delta and the crater rim lies a formation called the Martian unit. Starting in September 2023, Perseverance spent approximately 350 sols, nearly an Earth year, exploring this terrain. What it found there may be the single most significant geological discovery of the mission. The Martian unit is a band of olivine and carbonate-rich rock lining the inner wall of the western crater rim. Before the rover arrived, scientists had debated its origin for years. Some proposed it was a sedimentary deposit formed along the edge of the ancient lake. Others argued it was an igneous rock, altered after the fact by circulating water. The strongest orbital carbonate signatures in the unit fell within a narrow elevation range, between the level of the proposed lake outlet and a break in slope higher up the crater rim. This geometry had led some researchers to suggest the unit might represent an orthogenic lakeshore carbonate deposit. Perseverance settled this debate by revealing that both hypotheses were partially correct. The western portion of the Martian unit, closer to the crater rim and at higher elevations, turned out to be igneous. The rover found structureless to planar layered rock draped across the inner wall of the crater, with compositions consistent with an olivine cumulate. This is a rock formed by crystal settling in a large body of molten material, possibly a lava lake or a sill-like intrusion. The olivine crystals within this rock had been extensively altered by circulating carbon dioxide-rich fluids, transforming into iron and magnesium carbonates with a matrix of silica. This kind of alteration, the carbonation of ultramafic rock, creates environments that on Earth are known to support microbial life in the subsurface. But at lower elevations, in the eastern portion of the unit, the rock changed character dramatically. Here, the rover found well-stratified sandstones containing rounded, sand-sized grains of olivine and carbonate, cross-stratification, erosion surfaces. Bedding inclined both toward the center of the crater and back toward the rim, forming bimodal dip orientations. Convex-up structures with wavelengths of several meters. Trough cross-stratification with axes trending broadly east-west. These features are textbook indicators of wave action in a shoreline environment. In January 2026, an international team, led by researchers at Imperial College London, published their analysis in the journal JGR Planets. Their conclusion was striking. The eastern margin unit preserves the remains of an ancient Martian beach, a lacustrine shore zone where waves eroded and reworked the local igneous bedrock, rounding the grains and depositing them as sandy layers along the shore. They identified what appears to be a literal bar-like structure at a location called Turquoise Bay, striking parallel to the crater rim, with rimward and basinward inclined strata consistent with swash and washover processes. The ancient beach sits stratigraphically beneath the Jezero River delta. This means the calm, open-water lake conditions existed at this site even earlier than the delta deposition that followed. The habitability window at Jezero is longer than anyone had previously established. And here is the part that transforms this from a geology story into something much larger. On Earth, shoreline environments are among the most habitable places on the planet, and carbonate minerals that form in these settings have a remarkable property. They naturally seal in and preserve information about the ancient environment, including organic molecules. If microscopic life ever existed in the waters of Jezero, the beach is exactly where you would expect its chemical fingerprints to be locked in stone, waiting, possibly for billions of years. The rover collected 3 core samples from the margin unit. One of them, named Comet Geyser, was described by NASA as having the highest potential for finding preserved signs of ancient life of any sample taken during the entire mission. Those samples are sealed. They are sitting on the surface of Mars. And right now, there is no funded mission to retrieve them. But consider what the discovery of this beach actually means. For waves to form on the surface of a lake, 2 things are required. First, the water must not be frozen. This has been a point of contention in the Mars climate community for years. Many models suggest that early Mars was too cold for liquid water to persist at the surface, and that any lakes would have been ice-covered. The presence of wave-formed shoreline deposits directly contradicts that. At least for a time, the water in Jezero was open, ice-free, and in motion. Second, waves need wind. And wind needs atmosphere. Mars today has an atmospheric pressure less than 1% of Earth's, barely enough to feel, certainly not enough to drive waves on a lake surface. But the shoreline deposits at Jezero imply that the atmosphere was once substantially thicker, thick enough to generate wind, thick enough to push water into waves. This, in turn, strengthens the case for a warmer, wetter early Mars. Exactly the kind of environment where life could emerge. The east-west orientations of the bedding structures at Turquoise Bay are consistent with modern-day wind directions at Jezero, which are driven by slope flows developing along the western crater rim. Billions of years ago, similar winds may have blown across the surface of the lake, sculpting the shoreline and sorting the sediment. And there is one more detail worth noting. The researchers found that the candidate shoreline features exist within just a few meters of the elevation of the Jezero outlet channel. That outlet channel would have regulated the lake level, keeping it stable for extended periods. A stable lake level is the single most important factor in developing a well-defined shore zone. It means the beach was not a fleeting feature. The waves were not a momentary event. The shoreline existed long enough for the geological processes that formed it to play out over meaningful timescales. Then came the finding that made headlines around the world. In the summer of 2024, Perseverance descended into Neretva Vallis, the ancient river valley that had once carried water and sediment into Jezero Crater. Carved into the walls of this valley was a set of rocky outcrops collectively called the Bright Angel Formation. Light-toned, layered, visible even from orbit. When the rover reached these rocks, it found the finest grained sediment encountered in the entire mission: mudstone. Grains so small they could not be resolved by the rover's highest resolution cameras, indicating particles finer than coarse silt or very fine sand. On Earth, mudstone forms when fine particles settle through calm water to the lake floor. And on Earth, mudstone is among the best preservers of ancient microbial life. The mudstone was chemically distinctive. It was rich in silica, alumina, and iron oxide, and depleted in magnesium and manganese. This composition indicated that the source material had been chemically weathered and oxidized before being eroded, transported, and deposited. It was rusty red mud, the kind of sediment you get when rocks are exposed to a chemically active atmosphere, possibly one that included rainfall. But the chemistry was not the headline. The headline was what was embedded in the rock. Scattered throughout the mudstone were tiny dark masses, each about 100 to 200 micrometers across. The science team called them poppy seeds. Using the pixel instrument, they determined that these masses were enriched in iron, phosphorus, and zinc, with a chemical composition consistent with the mineral vivianite, a hydrated ferrous iron phosphate. On Earth, vivianite is frequently found in sediments, peat bogs, and near decaying organic matter. It forms through electron transfer reactions, where organic matter donates electrons to iron in the surrounding sediment, reducing it from its oxidized, rusty form to a reduced state that can combine with phosphorus. The Sherlock instrument detected organic carbon in several of the Bright Angel targets. A distinctive spectral peak, known as the G-band, appeared in the Raman spectra, indicating the presence of complex macromolecular organic compounds. These compounds can have multiple origins, including meteoritic delivery, abiotic synthesis in hydrothermal systems, and degradation of biologically produced carbon. But they were there, embedded in the mud, associated with the minerals that had formed through redox reactions. Then came the leopard spots. On a reddish, arrowhead-shaped rock named Chayava Falls, Perseverance's cameras revealed a striking pattern. Spots, each about a millimeter across, with dark rims and lighter, bleached cores. They were not sorted into layers or concentrated along bedding planes. They had formed right where they sat, in place. As reaction fronts, pixel analysis showed that the rims of the leopard spots contained vivianite, the same iron phosphate found in the poppy seeds. But in the cores, something different appeared. An iron sulfide phase with a chemical ratio consistent with the mineral greigite. On Earth, greigite is produced by sulfate-reducing microorganisms. Bacteria that consume organic matter and use sulfate as a terminal electron acceptor, producing sulfide as a waste product. The sulfide then combines with iron to precipitate greigite. The team pieced together a sequence. Organic matter in the mud reacted with the surrounding iron-rich sediment. First, iron was reduced, producing vivianite in the poppy seeds and in the rims of the leopard spots. Then, once the available iron was exhausted, a second reaction commenced. Sulfate in the pore water was reduced to sulfide, producing greigite in the cores. Each leopard spot was like a tiny chemical timeline, recording the progression from iron reduction to sulfate reduction, exactly the metabolic ladder that microbial ecosystems follow on Earth. There was an inverse correlation. The rocks with the most vivianite and greigite were the least red, the most bleached. The rocks with the least vivianite and greigite were the reddest, the the most oxidized. And the strength of the organic carbon signal tracked the same pattern: more organics, more reduced minerals, less red rock. In September 2025, the team published their findings in the journal Nature. Their language was careful, measured, and precise. The features they observed are consistent with biological processes but require more data or further study before a conclusion can be reached about the absence or presence of life. A potential biosignature. They considered the abiotic alternative in detail. Could vivianite form without biology? Possibly. The reduction of iron by organic matter can occur abiotically, though the specific experiment, incubating macromolecular organic carbon with ferric iron-rich mud at low temperature to produce vivianite, has not been demonstrated in the laboratory. Someone may yet do that experiment and succeed, but the greigite is harder. The reduction of sulfate to sulfide by organic matter at low temperatures is, in the words of the paper, exceedingly slow at temperatures below about 120 to 140 degrees. So slow that it is essentially not observed in natural environments on Earth in the absence of biology. And the bright angel rocks show no evidence of having been heated, no contact metamorphism, no recrystallization, no glass. The crystalline domain sizes remain at or near the detection limit, unchanged from top to bottom of the formation. The discovery was particularly surprising because it involved some of the youngest sedimentary rocks the mission had investigated. An earlier hypothesis had assumed that signs of ancient life would be confined to older rock formations. This finding suggests that Mars could have been habitable for a longer period or later in the planet's history than previously thought, and that older rocks might also hold signs of life that are simply harder to detect. The lead author of the study, Joel Hurowitz of Stony Brook University, described the challenge this way. The observations extend from outcrop-scale images down to the microscale of these little nodules and reaction fronts with their interesting mineral enrichments and organic matter. These could plausibly be explained by the activity of microorganisms that do similar things on Earth, but they might also have other non-biological explanations. That is about as far as anyone can be expected to go with a rover 200 million miles from any laboratory. On the confidence of life detection scale, a framework used by the astrobiology community to assess such discoveries, the team placed this finding at step 3 of 7. Step 1 is an interesting, potentially biological signal. Step 2 is ruling out contamination. Step 3 is establishing that the signal comes from an environment that could have plausibly hosted biological processes. Step 4, which the team says they are reaching toward but have not yet achieved, requires ruling out all known non-biological explanations. The acting NASA administrator stated that after a year of peer review, the reviewers could not find another explanation. This could be the clearest sign of life ever found on Mars. The sample, called Sapphire Canyon, is sealed inside a titanium tube. It sits on the surface of Mars. It may contain the answer to one of the oldest questions humanity has ever posed. If scientists could analyze it with Earth-based instruments, they could examine the iron isotopic composition of the vivianite compared to the surrounding mud. They could measure the sulfur isotopes in the greigite against the sulfate in the surrounding rock. They could look at the carbon isotope ratios between the organic matter and the trace carbonates, 3 independent isotope systems, each capable of revealing whether biology played a role. On Earth, when scientists study the oldest rocks for evidence of ancient life, isotopes are always where they turn. And this rock contains exactly the mineral pairs needed to run those tests. 5 years into its mission, Perseverance is not winding down. It is getting smarter. The rover has traveled nearly 25 miles across the Martian surface. It has collected 27 rock cores and several atmospheric samples. It has been cleared to continue operating through at least 2031. And, In early 2026, NASA announced that the rover can now do something it never could before. It can find itself. Since landing, Perseverance had tracked its position using a method called visual odometry, analyzing geological features in camera images taken every few feet while accounting for wheel slippage. But small errors accumulated. On longer drives, the rover's estimate of its own position could drift by more than 100 feet. When it calculated that it might be too close to hazardous terrain, it would stop driving and wait for instructions from Earth. Because radio signals take between 4 and 24 minutes to travel between the planets, that wait could cost an entire Martian day. Now, using a technology called Mars Global Localization, Perseverance captures a panoramic image with its navigation cameras and matches it against orbital terrain maps stored on board. An algorithm, running on a commercial processor that was originally installed in the helicopter base station used to communicate with Ingenuity, compares the terrain features and pinpoints the rover's location to within about 10 inches. The entire process takes roughly 2 minutes. It is, in effect, GPS for Mars. And it means Perseverance can drive for potentially unlimited distances without stopping to call home and ask where it is. The processor powering this capability is a commercial chip that runs more than 100 times faster than the rover's 2 main radiation-hardened computers, which are based on hardware introduced in 1997. Ingenuity proved that commercial processors could survive the Martian environment, and now Perseverance is harvesting that legacy. This came on the heels of another first. In late 2025, Perseverance completed its first drive that was fully planned by generative artificial intelligence. The AI analyzed orbital imagery, identified hazards including boulders, steep slopes, and boulder fields, and mapped out a safe route with designated waypoints. Engineers tested the plan on a detailed digital twin of the rover before transmitting the commands to Mars. A robot, on another planet, navigating terrain it has never seen, using an artificial mind to chart its own course. 5 years ago, this machine needed human operators on Earth to tell it every move. Now it plans its own drives and knows exactly where it is. NASA's Skyfall mission, announced in March 2026, plans to build on Ingenuity's legacy. The mission will use a daring mid-air deployment strategy to deliver a team of next-generation Mars helicopters to the surface. These helicopters will not be technology demonstrations. They will be operational scouts, tasked with surveying potential human landing sites and mapping subsurface water ice. The original Ingenuity was 4 pounds and flew for 90 seconds at a time. Its successors will be designed for sustained, purposeful exploration of the Martian terrain from the air. Ingenuity's final flight came on January 18, 2024, after a damaged rotor blade brought the mission to an end. But by then, the helicopter had already accomplished something far beyond its original mandate. It had proven that powered flight in an atmosphere less than 1% as dense as Earth's was not just possible, but reliable, repeatable, and scientifically useful. Every future aerial mission to Mars, and possibly to other worlds like Titan, will trace its lineage back to that first 30-second hover on a spring morning in 2021. And the commercial processor that ran Ingenuity's base station, the chip that was never designed for space, that was never tested against cosmic radiation, that was expected to survive maybe 5 flights and instead endured 72, is now the engine powering Perseverance's ability to locate itself on Mars without any help from Earth. The helicopter gave the rover a brain, and the rover is using it to explore further and faster than anyone thought possible. So where does this leave us? Perseverance has 6 empty sample tubes left to fill. Its radioisotope power source will keep producing electricity for years. The science is far from over. But the real question is not what the rover will find next. The real question is whether we will ever get to examine what it has already found. The Mars Sample Return mission The joint NASA and European Space Agency effort to retrieve those sealed tubes and return them to laboratories on Earth has faced repeated budget crises. The estimated cost swelled to $11 billion. In early 2026, Congress cut the program. As of today, there is no funded plan to bring the samples home. NASA's acting administrator has suggested there may be a faster, cheaper alternative, but no specific mission has been announced. China has proposed its own Mars sample return mission, potentially launching in 2028, and there has been speculation about private funding. But for now, the samples sit where the rover left them. 27 tubes of Martian rock, some from ancient lava flows that locked in the radiometric clock of Jezero's geological history. Some from the delta of a river that flowed billions of years ago into a lake that may have persisted for thousands of years. Some from the shore of that lake, a beach where waves once broke against sand under an atmosphere thick enough to push the water into motion. And one from a rock that contains a pattern of minerals that, on Earth, is most commonly produced by the metabolic activity of living microorganisms. The scientific community has been unequivocal about what needs to happen next. Bringing these samples back to Earth would allow analysis with instruments far more sensitive than anything that can be sent to Mars. Mass spectrometers, electron microscopes, isotope ratio analyzers, the kind of equipment that fills entire laboratories and requires teams of specialists to operate. The kind of equipment that could tell us, definitively, whether the minerals in the Bright Angel Formation were made by life or by chemistry. One scientist on the mission described it this way: "In that little tube, the answer might be there, whether we were ever alone in the universe." That sounds like a worthwhile legacy project for a space agency, a nation, or perhaps even a private individual willing to take on the challenge. For now, the tubes wait. The wind blows across them. The dust settles on them, and the question they might answer remains open. Here is what the data suggests so far. Mars was not always the cold, dry, radiation-scoured desert we see today. Billions of years ago, Jezero Crater held a lake. That lake was fed by at least one river flowing through a valley cut into the crater rim. The lake persisted long enough for a delta to build at its western edge. Before the delta formed, waves broke against a shoreline, rounding grains of sand and building small ridges of sediment along the coast. The atmosphere was thick enough to generate wind. The water was liquid and unfrozen. Beneath the surface, carbon dioxide-rich water circulated through olivine-rich igneous rock, creating the kind of hydrothermal environment that, on Earth, supports microbial life. And in the mud, at the bottom of a river channel that once fed that lake, chemical reactions produced a suite of minerals, vivianite and greigite, in patterns that bear a striking resemblance to what living organisms leave behind on our own planet. Some researchers believe this is compelling evidence that Mars once harbored life. Others argue that there may be abiotic processes we have not yet fully explored. What everyone agrees on is that the answer, the definitive answer, is sealed inside a titanium tube no bigger than a piece of chalk, sitting in the dust of an ancient riverbed on Mars. 5 years ago, we sent a robot to an alien lake and asked it to search for signs of life. It has done everything we asked and more. It outlasted its helicopter. It taught itself to navigate. It found an ancient beach no one knew existed. And in a piece of mud at the edge of a dried-up river, it found a chemical signature that no one can explain away. For now, all we can do is study the data, model the chemistry, debate the possibilities, and wait. Because somewhere on the surface of Mars, in the silence of a world where the wind still blows but no one listens, the most important sample ever collected in the history of science is waiting for someone to come pick it up. And it might hold the answer to whether we have ever truly been alone. What we know is already remarkable. In just 5 years, a single rover has rewritten the geological history of an entire crater. It has confirmed the existence of an ancient lake. It has mapped the architecture of a river delta. It has discovered a beach that nobody predicted. It has found hydrothermal alteration that could have supported subsurface life. And it has identified a chemical pattern in ancient mud that mirrors what living microorganisms produce on our own planet. What we do not know is whether any of it means what we hope it means. That is the nature of this kind of science. The data does not give you answers. It gives you better questions. And the questions coming from Mars right now are the most profound that any robotic mission has ever raised. Was Mars once alive? Did microbes breathe the iron and sulfate in the mud of a Martian lake 3.5 billion years ago? Or did some unknown abiotic chemistry, operating under conditions we do not yet understand, produce a mineral pattern that merely mimics life? The answer may already exist, sealed in a tube, sitting in the dust, 200 million miles from the nearest laboratory. Every answer brings another question, and that is how science moves forward.